Good morning, everyone. So today we have here the part B of limit cycles. Just to make a little overview, last video, we were starting to talk about limit cycles as a very special feature of non-linear systems. So it's impossible that you have a limit cycle in a linear system. Also, we discussed the fact that limit cycles are they don't have anything to do with fixed points. They are different. It's a different thing in nonlinear systems. And we also studied how to be able to discover a limit cycle in a given system, just making use of the phase plane and the so-called Poincaré-Bendixson's theorem. At the end of the class, we did this exercise also with a van der Pol oscillator when we wanted to compute the period of the limit cycle. The idea of today's video is to talk about perturbation theory and how this theory can help us in computing, quantifying characteristics of the limit cycle, like for example frequency and amplitude. Therefore, we will have to start with something that is simple to study, but at the same time is nonlinear, because if we lose this nonlinearity property of the system, we will not have any limit cycle. So we will talk about weakly nonlinear oscillators. You will see that the methods enclosed in this perturbation theory are very efficient and they apply very well to this kind of systems. So we have, for example, an oscillator. So you just discover here the second order derivative in time, and here the zero order derivative, and in addition there is a function that can be nonlinear in x and x dot, for example. Eventually can be more than that as well. The important part is that this is weighted by a constant that is very small. So it means that the contribution of this term to this is actually small. However, it's enough already to capture limit cycles. And what is perturbation theory about? Is very simple. It's simply being able to decompose the quantity of interest, for example this x, as a combination of different orders. For example, the most important part in here, the one that contributes the most, is this one. This is the zero order x. Then you will have, if you can call it correction, of order epsilon, and then an additional one of order epsilon to the square, and eventually you can go like this until infinity. Most of the time, when you just want to know the essential features of the limit cycle, you just care about frequency and amplitude, for example, at a given time. You will consider maybe, okay, the zero is important, the first and maybe the second order. That should be enough, okay? The key part is that instead of having just one solution for x, we will have three solutions. Actually, we have three equations that need solutions. We will find first the solution of x naught. From this x naught, we will use it to find the solution of x1. From this one, we will be able to have the solution of x2 and so on. It's like a cascade. So we will do this example. This is just strange at first glance because we are just talking about a linear system, and this linear system doesn't have any limit cycle. Okay, so I mean this is not of interest, let's say, for studying limit cycles. However, in order to introduce this perturbation theory, it's of interest to have a little investigation in this small equation. Okay, also something interesting is that this equation has a analytical solution, as you just see here. Okay, therefore we will be able to compare the results of the perturbation theory with respect to the actual solution, which is given by the analytical expression here. So the interesting here is to solve this equation by perturbation theory. And we will just do this decomposition in orders. So we will just care about 0 order and first order, and that's enough. So this is approximation. Okay, so we're just given by these two terms. So what we have to do right now is to define also what is x dot. This is just a linear operation, so it's easy to see that x dot is just x0 or x naught plus epsilon x1, and the same thing for x dot dot. Okay, nothing complicated. And what is next then is just to introduce all this in here. So it's going to be a long expression, but it's nothing out of this world. So let's write it down. So we start with x dot plus epsilon 1 x dot naught plus 2 epsilon x then plus epsilon. Okay, this is here is 1. Okay, so we have just done the decomposition, and now the important part, and that's why we need epsilon to be small, is that we assume that the magnitude of perturbations, let's say, they do not, so the large perturbations do not talk with the small perturbations, and these do not talk with the very super tiny perturbations. They are like in different scales, living in different worlds. Therefore we can do the decomposition as follows. We will just factorize first order 0. Okay, order 0 means we have epsilon 0, and then we will have x plus x 0, and that's all. Okay, and then order epsilon 1, we will have x1 dot plus x1, and then this one in here and this one in here, and this one actually not, because this is already second order, so this would be for another equation. So this one is gonna be minus 2x0, and that's all. So just to say, we have here 6 terms, we have here 5 terms, because this term do not enter into the game, because we are just considering epsilon 0 epsilon 1. Okay, so we have the problem of interest, and these are the questions we have to solve. This has an analytical solution. This is an oscillator that is non-damped, so non-damped oscillator, and we can have the solution in this form. So we have a sinus of t plus b cosinus of t. Since we need also the information of x dot here, we can just do it right now. So x naught dot is equal to a cosinus of t minus b sinus of t. So I think it's a good moment to apply the initial conditions in here, so that we just somehow shrink this expression, and the solution of the second equation here is going to be simple. So, or let's say simply means that like shorter. So let's apply these conditions to this problem. These conditions can be also splitted as 0 and first order. So if we have x0, we can say that this is equal to x naught 0 plus epsilon x1 0, and here x dot 0 is equal to x 0 plus, yeah, and this is equal to what? So the first one is equal to 0, and this is equal to 1, which means that this is equal to 0, and this is equal to 0, this is equal to 1, and this is equal to 0. So see that this is actually of a scale of epsilon of 0 order. Therefore this one is assigned to the scale of 0 order, and this one, this is just a remaining part, so like a residual if you want. Then this is gonna be just 0. So based on these conditions in here, we will be able to solve this equation. So let's just replace the initial conditions to the equation to find the values of a and b. Let me just put in here. Then x0 is equal to what? Just b, and this is equal to, if you look in here, to 0, and x dot 0 is equal to a, and this is equal to 1. So from this we know that x naught is nothing but sinus of t. So we will just write this here. This has already a solution, which is x naught is equal to sinus of t. Now we go into the second equation and we want to solve it. Then we have minus 2, actually we can just do it, minus 2 cosinus of t, okay, derivative of this. So the characteristic solution of this equation is not the same as this one, because now we have a forcing term in here. So you just look into the literature on internet, you just find that the solution is just given by x1 equal, let's call it, I don't know, ct sinus of t plus bt cosinus of t. So this is the solution of x1. Okay, so now we have to do the derivative of x1, so x1 dot and x1 dot dot based on this expression. So basically similar to what we did before. So this is x1 dot equal to zt cosinus of t plus c sinus of t minus bt cosinus of t plus b cosinus of t. Here is sinus. Okay, so right now we can already replaced the initial conditions. Remember that we had, I will just put it in here just to remember. Okay, we have here the initial conditions, and in order to avoid a super huge expression for x1 dot dot, we can just replace the first one, which is this one and this one. So here the first one is, it doesn't give us information, because if we replace x1 in 0, automatically this goes to 0, and then c and b remain. We don't have any information from that, but from this one we do. So we just have that x1 of 0 is equal to what? To b, and this has to be 0, so b is 0. So we can simplify this expression already from that condition. Okay, so we just erase this, okay, and we can go on to the x1 dot dot. So it's equal to what? This is c t, then minus sinus of t plus c cosinus of t plus c cosinus of t. So this is just 2 cosinus of t. Okay, so this is, we can just sum the whole thing here, 2c cosinus of t. Okay, now finally we will just replace this expression. So here x1 dot dot, the thing we just wrote here, so minus ct then we have this one, which is this one, and finally the right hand side. And from this expression we already know the value of the constant, so this one goes with this one, and this one has to be the same as this one. Therefore c has to be equal to what? Minus 1. Yeah, so we write here the solution of this equation is x1 equal to minus t sinus of t. So we just remove this, we don't need it, and we write then the solution of our problem, which is x is equal to x0 plus epsilon x1, which is sinus of t minus epsilon t sinus of t. So our hope is that this solution is actually very close to the analytical solution, which is the reference one. Okay, now let's go to the next slide, and this is what we obtain. And this is a little bit like bad news, all this work for nothing. Look, this exact solution, so it's just, imagine a sinusoid that is being damped by an exponential decay. So this is something close to this, and the perturbation theory solution, so this thin line is actually behaving pretty well at the beginning, but then it starts deviating and just explodes eventually. So what does it mean? Okay, now if we look more into the mathematical perspective, you will see just this term eventually explodes. This as times goes to infinity, this expression goes to infinity. Okay, and this is actually, if you remember, this came from the solution of this equation, from this equation. And now we look at closer, you will realize that this is an oscillator, again, without any damping, and we are applying a forcing term at the frequency at the natural frequency of this oscillator. The natural frequency of this oscillator is 1 in here, and the oscillation is also at frequency 1. So we are actually imposing a resonance into the equation, to the system, and this manifests as an unbounded solution when time goes to infinity. You will see that in the future, as we'll talk about this thing doesn't have to exist, otherwise we will have trouble. This term is called resonant term, or also recognized as secular terms in the literature. Maybe some of you may think that maybe we need to expand to a second or to a third order to have a better agreement with the analytical solution, and this is actually a sort of correct answer, because if you increase the number of terms in the expansion, so just epsilon order 2, epsilon order 3, and so on, you will realize that you will be able to cover more and more. So the agreement is going to be every single time larger and larger. But eventually, perturbation theory, regular perturbation theory, will fail. And this is actually something that many people discovered tens of years ago and proposed an additional, somehow, a fix on this regular perturbation theory to make it work very nicely. The first thing is, when you look at the solution, you realize that there are two time scales. So you have the time scale in which the oscillation actually is happening, so this frequency, so this period. And the other time scale is somehow ruled or governed by this decay. So you can imagine this like an exponential decay that happens in slow time. So we will see also that having two time scales will allow us, so it will give us a degree of freedom to be able to eliminate completely any secular terms in the equations. So here is one by one the comparison, the true solution and the approximated solution. So there are very strong differences. So the appearance of the two time scales, so this is the slow time you see here. So this is the envelope, the exponential decay envelope, and we have here the time of the oscillations. And additionally, we see that there is a slight shift in the frequency. So here the frequency is 1, here the frequency is just a little bit less than what given or depending on the value of epsilon. The main message here is that we need to account, or a technique that allows us to account for this slow time and this, let's call it fast time. Okay, so by doing so, you will realize that we don't need to go very high in the order, in the expansion of x, but we just need to account for these two time scales. So this now we will solve exactly the same problem, but we will make use of these small and time scales. Okay, two timing expansion. So we have two times. We have the so-called fast time, which is going to be just considered just as tau. So they are basically the same. And the slow time, this is the new time that we introduce into the analysis, which is just the time scale we have right now multiplied by a epsilon. So now we have two arguments. We have tau and capital T, but the rest is the same. So we have the zero order scale, the first order, and higher order terms collected in this big O. So this, and now compare this with this. So you just see the difference. We are considering 2 time scales instead of just 1. And the first thing we have to do is to just define the temporal derivatives. So the first order derivative here with respect to t is going to be, this is just a total derivative, because in here we have just 1 time scale. However, we will have now this converted into the partial derivatives when we have 2 time scales. So you can just see here that we just applied the chain rule. So just remember the x d tau dt plus the x d capital T dt. So, and this is basically just the chain rule. Let's remember what we just defined before. So we have tau is equal to t, and the slow time is capital T epsilon t, like this. So based on this, we can know that what is the value of this one. So this comes from this one in here, so this is just 1, and this one here is what? Yeah, it's epsilon. And this is how this first order derivative is defined. And now that we do the decomposition, so x, remember the perturbation theory, is equal to x naught plus epsilon x1, then x dot in here is equal to the tau x naught plus epsilon t x naught, and now we go to x1, so epsilon the tau x1 plus epsilon square x1, and we just keep these terms, and the second order term in epsilon we just discard it. Okay, so this second order derivative is a little bit more involved. So let's start again with our definition. So x, this is equal to the x plus epsilon here, the tau x. So basically this is an operator, so this is approximated equal to x. So this is the operator we want to here introduce. So if we have actually then a second order derivative is just this operator twice. Let me just write it down. And then this is this operator on the first order derivative and then we just do the corresponding operations. So this is second order x plus epsilon second order tau tx plus exactly the same thing plus second ordered like this. So again we keep these ones, the one is 0 and the first order, and this one we just discard it. We are just keeping the first order terms in epsilon and the 0 order. So
Remember, this is just approximation, and then we keep approximating. We do plus 2 times epsilon, and finally we just replace x0, so the composition x equal x0 plus epsilon x1. So we have times epsilon, and now we have also this one, x1. Okay, so just to not confuse people, I will just somehow use the same notation right now, equal to the one of the following slides. So just allow me to erase this. And instead put this second here. So finally we have the main ingredients, which is how to express x dot and x dot dot in terms of x naught and x1, but also in terms of fast and slow times. So let's go back to the previous example and discuss it. We have this linear differential equation, okay, and we decompose it, so x naught epsilon x1, and then we just express as well the corresponding derivatives, first order derivative in time and second order derivative in time. Then we just put all this in here in this expression, and we just separate what is order epsilon 0, order epsilon 1, and we just solve the equations independently. So this is what we did, but remember that in here we have this dangerous term, which is the circular term. This is going to be maybe more clear in the following slides, and this is the thing we want to eliminate. So we will start by doing basically the same thing, but now we will take into account the two time scales. So as you see here, then we just have replaced these expressions by these ones. Now things are a little bit more involved, they are a little bit more complicated, but this is just because we have more terms. And we proceed exactly the same as before, so we just replace the expression, these ones, in here. So I will just do it offline. Okay, so here it is. We have the terms being replaced, x dot dot to epsilon x dot plus x. And what do we have to do now? Yeah, we have just to reorganize the whole stuff in orders. So order 0 epsilon, order first epsilon, and the higher orders we could eventually keep them, but for simplicity and also because we don't need more, we just discarded and we just considered two levels, epsilon 0, epsilon order 0, epsilon order 1. So order 0, we have this one here, so tau t t x naught, then we have no, and this one in here, plus x not equal 0. So this is epsilon order 0, and now the order 1 is gonna be, we start with this one, t total 1, then this one plus 2 dt tau x naught plus 2 then t tau x naught. The other one is second order, so we don't get it, so we don't keep it. This one is also second order, we don't keep it. And we finish with plus x1. And the idea now is to reorganize these equations. So just to put at the left hand side what we don't know, and at the right hand side with what we do know. So here there is nothing at the right hand side, so this will have to be solved, and from this we will obtain x naught, and x naught is actually in here 2 times, and we will put this at the right hand side. So this is actually x1 plus equal minus 2 times, then we have here t tau x0 plus t tau 0. So we are in a very similar position as before. We have to solve this equation, which is exactly the same. Remember? So what is the solution of this equation? We have said that is a sinus of, so this is in the first time we did it. But the question is this actually correct, or how this is related with this one? So the first thing we have to see is that the variable, the independent variable is not anymore t, is tau. This is going to be the fast time. So this is already something we have to replace. In here is not t but tau. Okay. And the other thing that I have to say is the most crucial thing of this part. Remember that x naught in here is function of two times scales. So the fast time scale is tau. So I'm asking, what is the slow time? So the capital T. Where can we find the capital T in this equation? Yeah, some of you may be already guessing. So before we have considered this A and this B to be constants, so they will not change ever in time. Now we will allow these variables, so these A and B, to be function of a slow time. So this is the major feature that you should not forget. So remember that x, so I will just write it explicitly, depends on tau and t, and now we have A is t sinus of tau plus B t cosinus of tau. And now this one has to be replaced, so this quantity in here, this is the term that we are supposed to know already. Now we have first to derive these two derivatives. Okay, so let's start with the last one. So we want to have d tau x naught. So this is simple. I think, what is the first one then? So we have a capital T, so the derivative of sinus is cosinus, and in here we will have minus b t, the derivative of cosinus is minus sinus. And now let's go to the second one in here. So we just have to derive this by capital T, d tau t x naught. So the derivative of this is just dA dt cosinus of tau plus dB dt sinus of tau, and that's all. Now let's call this, so the right hand side. So the right hand side is equal to minus 2, and then we just write this down. Okay, plus b, and then plus at cosinus of tau minus bt sinus of tau. And remember that this term in here, how is it called? I already have said it like sometimes already. This is called the resonant term, or in other words, the secular terms. But okay, attention, not everything that is at the right hand side is a secular term. It has to be a function that is excited or is oscillated at the same frequency of the natural frequency of the left hand side. So in here, what is the natural frequency of this oscillator? Yeah, is 1. And the natural frequency of these oscillators is also 1. Okay, imagine you have here omega tau. So this is omega is equal to 1. So in this case, all these 4 terms are resonant or secular. There might be cases when you have actually maybe harmonics or just other frequencies, then these are actually not secular terms. So in this case, all of them are secular terms. And what do we do with them? We need to make them vanish. And therefore, we will oblige these terms to be 0. Okay? So now then, we know we have to make them 0. And we can group these 4 terms into groups. So the group of sinus and the group of cosinus. So let me just write it in here. The first group is going to be dA dt cosinus of t plus a t cosinus of t has to be 0. And the second one is basically the same. Plus bt sinus of t has to be 0. So from this one, we already know that we may have a differential equation. Maybe you already got it. The a dt is equal to minus a, and here we have dB dt equal minus bt, and this is a very simple first order differential equation. We already know how to solve it. Okay, so just remember, just the idea is to connect all the dots that we have already in our minds. This is nothing by this, I mean, in the classical notation we use with x, and this is an equation, and what is happening here, what is this? This is the growth rate. So in this case, the growth rate of this equation or of this variable a is minus 1. Okay, so let me just, this was just to make like a parenthesis, no? This is a parenthesis. So we know already the solution of this equation is at is equal to minus t. Although there is something missing, we have to discuss about what is missing. Yeah, what is missing is actually that the solution of this equation can be just any constant multiplied by the eigenfunction. So the eigenfunction is just one dimensional, therefore it's just one. It's in here, and this is the other. I mean, it's the same eigenfunction, but for the other variable b. So what is missing in here is the constant. They don't have to be the same, so we'll just put it. Let's put c1. Sorry, let's put c1 and c2. Okay, so we're back. We have the solution x naught, and we have the solution of the constants that are actually not constants because they depend on the slow time, which we just found by making the secular terms vanish. So right now, if this is actually what we're looking for, we will be sure that we will not have any resonance happening, and maybe hopefully we will have a correct approximation of the solution. But there is something missing. We don't know the values of the constants here, c1 and c2. And if you realize, we haven't actually made use of the initial conditions of the problem. So let me just write them down in here. So maybe now we have to do development to be able to relate these initial conditions, which are for the classical equation, so there is no perturbation in here, to these equations, which are the perturbed equation, and also they consider fast and low and slow time scales. So let's start with the first one. What is x naught? So this is going to be translated to actually x naught. So this one is gonna be the fast and the other one is gonna be the slow time, and this is going to be just x naught 0 0 plus epsilon x1 0 0, and for the other one we'll have x dot 0 is equal to, so if we go back to the previous derivation, we will realize that we have this case plus epsilon, and this is happening at 0, and this one at 0, and it has to be equal to 1. But we have to actually decompose it first, so as well. So the x naught plus the x1 epsilon plus epsilon the x1 0 equal 1. Okay, so let's go back to the first one, to this one. I didn't write it in here, so this is 0, this is 1, this is 1, and this is actually then 0, this is 0, here this is 1, and these are 0, because these are this condition in here. We see this is order 1, therefore this is going to be assigned to this one, and this one are simply given as 0. So let me just derive again this quantity in here to apply the boundary condition. We have the x naught the tau at 0 is equal, so let's do it first, then is a cosinus of tau minus b sinus of tau. Okay, and now we do x, and then remember this is at 0 0. This is gonna give us a0 cosinus of 0 minus b0 sinus of 0, and this is gonna be 1, this is gonna be 0. So basically we say that a at 0, so this is, remember that this is t, so when t is 0, a 0 is equal to 1. Now if we do replace the first initial condition, actually I haven't done it, this one, then we will have a0 0, sine of 0 is gonna be 0, and this one b0 will have to be 0, so that this term actually vanishes, because after replacing, remember, this is going to be b0 cosinus of 0, so at time 0 0. Therefore this has to be 1, this is 0, and at the initial condition this is going to be 0, therefore this term has to be 0. Okay, so we have basically everything, just so that things make sense. This is equal, a0 is equal to c1. Okay, you can just see it in here. This exponential to the minus 0 is 1, therefore this is going to be equal to 1, and this is equal to c2. So the solution reads x is equal to x naught plus x1, and if you realize, we didn't solve the equation for x1. What we did was just to replace the circular terms and to make them 0. Eventually we could solve the equation and add an additional equation of epsilon to the second order to cancel additional secular terms and so on, if we want to recover this x1. Right now, however, we will just be happy with the solution of 0 order. So we will say we have x, this is approximated to x naught, which is actually a t sinus of tau, and this is exponential minus tau sinus of t. Now if we replace the definition, remember we have tau is equal to t and capital T is equal to epsilon tau. Therefore we will have something like this, and this is the approximation of the solution of this equation. Okay, so right now, remember, we are just understanding or learning how to do perturbation theory, and the objective of all these things is to be able to solve nonlinear differential equations, to be able to investigate frequencies of the limit cycles, amplitude of the limit cycles, and so on. But in order to start understanding this perturbation theory, we will just evaluating first order differential equations, second order differential equations, but linear differential equations. So this actually has a analytical solution, and our objective now is to compare how close is this approximation to the actual analytical solution. Once we are happy with this, we can actually investigate nonlinear ODEs. So in the slides that you can find in Moodle, all this is written in a more, let's say, neat way. So it's LaTeX. Okay, and now we have here this comparison. This is something we just shown in the previous exercise with regular perturbation theory, and this is to show you that the zero order approximation, which is this one, we just wrote it down, matches very well the exact solution. Okay, so you remember for regular perturbation theory we had something that was actually growing until infinity. Now we have something that matches very well the exact solution, and we can see that the role of the slow time is just to somehow impose this exponential decay in this envelope, as you see here, governed by this. And the fast time is just the one given the oscillatory behavior of the solution. Okay, now we go to the so-called average equations. This is basically the same we just did with two-time scales perturbation theory, but is systematized. So you already have like a set of steps to follow, and you don't have to repeat things, but you already somehow base yourself on a final set of equations, which are integration equations. So let's go. So here we see the same. So we see a given differential equation. In here, this is written in a very generic way. So this term, the idea is that it's nonlinear and that it depends non-linearly in x and x dot. But also you could use it for the example we had just with this linear differential equation when this was just a function of x dot. But let's forget about the actual function. We just say this is a nonlinear function in x and x dot, and the process, so the methodology is the same. We just split everything in terms of zero order and first order in this case. So again we have these are like pure oscillators for x naught and for x1, and here we have the right hand side that is exciting this oscillator in here. And what we did before, we had just the explicit expression for this thing, and we just identified the secular terms. We happen to be all of them, and we make them vanish. Right now we have basically the same thing, and we have a term called h. So h is this function in here. So here you see already the first change in the whole thing, because here h by definition is x dot. But now since we are in the epsilon terms, here we have to keep the zero order. So x0, so x naught, and the derivative of x naught. And eventually, if we want to have a second order in epsilon, so a third equation, in that moment we would add x1 and partial derivative of x1, okay? But we will focus as before on these two equations. And as before, we look for a solution, so the archetypal solution for this oscillator in here, which we did and we collected as a linear combination of sinus and cosinus. This is the solution we used before. But in order to make things in a more systematic way, as I will show you in these slides, then we will consider another way of expressing this solution, which is in polar coordinates. So this is the solution with the polar coordinates. We will need then to find a given amplitude and a given phase. Still we have two variables that depends on the slow time, t. Before we have a and b, now we have r and phi. So reminding the definition of h, that depends on x naught and the partial derivative of x naught. Then we just need to replace this in here. Okay, so this is gonna be the same, and here we just do the derivation. And this is what is obtained. Now the last step is assuming the shape of h, okay? And we will say that h depend on first theta. Okay, this is just a transformation, so we just collect this tau and phi in theta as in here. And also we say that this is h can be expressed as a Fourier series, so we just make an infinite sum of cosinus and sinuses. Since this is a Fourier series, we have already the expression for the Fourier coefficients, that in this case is ak and bk. And voila, this is it. So we have a naught, ak and bk. This is what is of interest. But now we have to pay attention. We have to already start suspecting that not every single term in H is going to be a secular term. Remember that the secular terms are the ones that oscillate at the frequency of this oscillator, and the frequency of this oscillator is 1. Therefore, the terms that are gonna be important for us are the ones with k equal to 1. The rest we do not care. So we start building the right hand side. So this one is just derivative, so this is something we can do, and we obtain, well, the actual derivative. So we have sinus, cosinus, and remember that r and phi are slow time, and this dash is what represents the derivative of r with respect to capital T, and the same derivative of phi with respect to capital T. So we have this expression, and now we have h, and as I told you before, we will just keep the coefficients with k equal to 1. And then we can just factorize the whole expression, and we have two terms that are going to represent the secular terms, these two, and then we have to do this term 0 and this term also 0. So now we have to remember which is the actual expression for these two Fourier coefficients. So this is the equation we want to solve, but we need the definition of a1 and b1, and here it is. So we have a1 and b1. Okay, so, and this is the function h with respect to theta. And these equations are called the average equations or the slow time equations. These are super famous in perturbation theory, or when you talk about nonlinear oscillators. There are a lot of studies that make use of these two equations. And remember, they are called slow time equations. I prefer that name than average equations. So slow time equations, because it gives you the dynamics of the slow time. So in this case, r dash and r phi dash. In the book of Strogatz, you can find again the example we did just before, this linear differential equation, by using these average equations. This is much more straightforward. It's like, I don't want to say that it's applying a recipe, but as long as you understand how the recipe is built, then yes, it's just having these equations and getting straight to the answer, because you just need an integration. So you can revise this example in the book of Strogatz, but we will jump already to the van der Pol equation, which is the thing we are interested in. Remember, we want actually a non-linear differential equation so that we can have actually a limit cycle and then study the amplitude and the frequency of the limit cycle. Okay, and this is the example. We have this van der Pol equation, and this is the term we want to pay attention to, is this term h. And remember, we are talking about weakly nonlinear oscillators, okay? Therefore, we have this epsilon here. As I pointed out some slides before, we need to have weakly nonlinear oscillators because we need somehow the difference of scales in order to use this perturbation theory. So we have the definition already of x. This is the thing we already had. So remember, there's x is equal to r cosinus of theta, and we just apply this to the actual expression for h, and we obtain the actual derivation. So r cosinus of theta, this to the square, minus 1, and the derivative. Remember that when we are talking about x dot here, we are talking about derivative with respect to tau. Let me just write it down. Okay, so this is the definition of x dot with respect to tau and capital T. But remember that in the second equation is where h comes into the game, and the second equation is already, remember, this is already weighted by epsilon. Therefore, we need to have only first, let's say, zero order terms, which is just this one. Okay, so in these two cases, these two terms, they vanish, and we will just have x dot to be the derivative with respect to tau, and therefore here we just derive with respect to tau, and tau is inside theta, so this is the transformation we just did before, and therefore we obtain this. So the objective, as you may already suspected, is to find the equations for r and phi. So these are the slope variables. Therefore, we need a differential equation, and this is obtained by solving these two integrals. Okay, so let's go first with r, and we will see then it's equal to 1 over 2 pi from 0 to 2 pi, and then we have h, so r minus 1 minus r sinus of theta, then multiply by sinus in here, and this is obtained, then sinus of theta d theta. So we have to solve this equation, and the other equation is going to be, so r phi prime so the same thing. Okay, and then we get this, so it's the same, but now we are multiplying with respect to cosinus of theta in here. Now we have to solve these equations. So in the class, normally what I do is I go to Wolfram Alpha, so to the internet, and try to find the analytical solution for this expression. Okay, you can do the same, you can do it by hand, but I will just provide right now the solution of this equation. Okay, now I just put these expressions in here, and this is the first integral, you can just see, and this is the second integral in here. So I split each integral in two, and now we have that for this integral we have that this is equal to minus r cube p over 4. This is equal to r pi, and these two are actually 0. So from this we have that r prime is equal to 1 over 2 pi of minus 3 squared p4 plus 3 pi, and this is equal to r prime equal to 1 over 2 minus r to the cube plus r, and the other one here is just simply phi prime equal to 0. So these are the two equations that describe the evolution in time, so of capital T of r and phi, so of the amplitude and the phase. Okay, so let me just write the solution again. So we have x is equal to x0, so approximately x0, and the epsilon was just discarded, and this is equal to r of t cosinus of tau plus phi t. Okay, so we can go and ask the question, what do we want to know? So we want to know the actual expression, which will be very elegant. We can do as in Strogatz and just solve analytically this equation. Okay, it will take some time, but we can just have an expression for r. But if the question is just what happens when t goes to infinity, we can just actually make use of our knowledge on flows on the line, and we know that r dash, so this one will not change anymore if we find the fixed points for this case. Okay, so in order to find the final amplitude of oscillation, we eventually just have to find the fixed points for this one. So let's say when r dash, so let me just write it like in this way to make it more like explicit. When this is 0, it means that we have r factorize 1 minus r to the square over 4 equal to 0. Then the fixed point is going to be 0, and the other one is going to be r to the square is equal to 4. Therefore the fixed point, the other one is plus minus 2. So actually, just to have a more, let's say, overall idea of the behavior of this equation, so we can just plot it as well. So I just did it with Desmos. I will just put this in here in a schematic way. So we have here 0, 2, minus 2, and then we have the function looks like this. Okay, so the only information that we are missing is the actual initial conditions that are used. So the initial conditions, I will just write it in here. This is just the definition of the problem. So x0 equal 1 and x dot here equal 0. So if we transform these initial conditions to the two time scales, it means that we have x of 0 0, which is equal to x 0 0 plus epsilon x1 0 0 equal to 1. And in here we can just say this is equal to 1 and this is equal to 0. And the second initial condition is then x dot 0 0, which is just the x the tau plus epsilon the x dt plus epsilon the x1 the tau, and this is equal to 0. So that means that we have this is 0, this is yellow, 0 0 and 0. So we have two initial conditions because we have two first order differential equations. However, one differential equation is already solved. It's basically just a constant. And the other one is this one here. But just have in mind that we have the initial conditions, but on the variables x naught and the derivative, but we need the initial conditions in terms of r and phi. So we need a last transformation. So we need this transformation. So let's focus right now just on these ones. And we know we can draw this in a polar coordinate. So we have here x, let's call just x. Here we will have x dot. And you already can see that a given value here, you can represent this in the polar coordinates. So you can have r, and this is gonna be theta, which is, remember that this is tau plus phi. So here we have that r is just x squared plus x dot square. And that phi is nothing but -1 of x dot x. So for the first equation here, we can say that r of 0 0 is equal to x 0 0, which is basically just 1, and here is 0. No, sorry, here 0. Okay, so r 0 0 is 1. Okay, I need to be a little bit more specific in here. So remember that we are talking about this equation. So r is expressed with respect to x naught only. Therefore, this is something I have to clarify in here. X naught. Okay. And this one is equal to 0. So from this expression, we know that the phase starts at 0 and remains at 0 forever, and r start at 1. So r is gonna be, I don't have here the axis, this is maybe dangerous. So this is gonna be the r dt, and this is r. So r starts at 1 and then just is get attracted to this fixed point, and it will remain, then it will reach 2 asymptotically as t goes to infinity. And this is actually the question we wanted to answer. Okay, we can go to another example. This is the last example of this session, and we will talk about the so-called Dolphin oscillator. Okay, so this is also a very classical oscillator in addition to the Van der Pol, and it's characteristic because of this. So it's a nonlinearity, and it does not have any time operators. It's just x to the cube. This is again the archetypal construction. Therefore, we can just have to find h with respect to x, and x is equally expressed as r cosinus of theta. Then we get this one. Okay. And again, in this limit cycle problem, we want to find an approximation for the amplitude and the frequency. Okay, so we just need to replace here again h. So r prime is equal to 1 over 2 pi 0 to pi r cube cosinus of theta sinus of theta d theta, and r phi prime equal to 1 over 2 pi 0 to pi r cosinus of theta. Actually, this is cosinus 4 d theta, and this is equal, so this is 0, then we have here r prime is equal to 0, and this one here, this is equal to 3p4. Therefore, we have here r phi prime equal to 1 over 2 pi 3p4, and we have 3 8. Again, miss here r cube. Okay, so we have actually the opposite problem as before. So at the initial condition, at a given amplitude, will remain like that with the same amplitude, so r. And in here, okay, here we can simplify things. So phi prime is equal to 3 r squared. So in here we have an equation with respect to the small times, the slow time, capital T, and this is an equation for phi. Well, equation for the change of phi, because this is prime. Therefore, we already can have an idea of what is happening with the frequency. Okay, if you remember, so if I just put something like sinus, this is a given example, sinus of theta. So we see here this is an angle, theta is an angle. Also, you can see that in the polar coordinates. And now we can see how this angle changes in time. Okay, and this change in time of the angle, so let's put it theta dot, is nothing else than the angular frequency. So just, okay, parenthesis, we cannot have the same analysis as before because this ODE has two different variables, phi and r, so we cannot just rely on this flow on the line. But now we face the problem in with a different perspective, from this definition, okay? And we know that the theta for our case, so if I write the whole thing express, oh no, actually it's in here. Well, actually I will write it. X is equal to R. No, this is just R, sorry. R cosinus of theta. And then we have R. This is actually, if we go backwards in time, we realize that we had this expression before. Okay. This is constant, so this is, for this example in particular, we know that this is constant. Therefore, we can just replace this and say that it remained from the beginning the same, so R naught. And this is actually theta. Now we have to evaluate theta. So theta dot is equal to omega, and d theta dt. Okay, this is maybe just redundant, but just to remember that we have this chain rule, d tau plus epsilon. Sorry, this is theta dt. So the first one is, this is simple because we have this. So with respect to tau, we have here, this is 1, and this one is also simply obtained. So we have that d theta dt is actually d theta d phi dt, and this one is 1. Okay, so we just need this one, and this is actually the thing we just found out before, which is, this is the change with respect to capital T, remember the derivative. So this is 3r cube square. So what I wanna say, maybe let's just put this thing in here. Omega is equal to 1 plus epsilon voila. And what does it mean? That the amplitude, so the frequency of this oscillator, it depends exclusively on the amplitude. So if you start with a very small amplitude, R naught, the R naught remains like that forever. So we can actually put here R naught, and the frequency is going to be close to 1. Okay, this is epsilon, so anyway, it's going to be always close to 1. But what I mean is, if R is larger, this contribution is going to be larger, and the frequency is going to increase. So the higher the amplitude, the faster it rotates, so, or it oscillates. Okay. Well, guys, so this is the last part of this session of limit cycles. I hope you have enjoyed it. The last it was pretty mathematical, this perturbation theory part, but it's important when you want to study nonlinear systems. So nonlinear ODE is actually super helpful, and it's nice to know it. So next class we will go into the phase plane in 2 dimensions. This is going to be also very interesting, and because we will just focus on bifurcations. Okay. And well, that's all, and see you next class. Okay, bye bye.